Welcome back to this channel. So in this video we are going to be handling applications of differentiation. So this video is presented to you by Yusuf, and it's going to be handled in about 6 parts. So you're going to be starting with maximum and minimum as applied in differentiation and pure mathematics. So when you're looking at maximum and minimum, we are also going to be looking at inflection points. So first of all, we are going to first be going with their sketches so that you can understand or differentiate between a maximum, a minimum, and also a point of inflation. Now these ones will be further magnified under a subtopic called curve sketching, which is under applications of differentiation. So first of all, the point of maximum is where we are having a peak. So we call this one the point which is here in terms of a coordinate. Let me say xy. This is what we call a maximum point. And on this graph is going to be represented by point A. And then the minimum is that point which forms a low. So point here is what we call a minimum. And this is represented by point B on our curve. Now a point of inflation is where we don't have either. It's a point which combines both a maximum and a minimum. So you find that here, instead of this curving to go downwards, it's just going to go upwards. So you're having one half of a minimum, and you're having one half of a maximum. So this one becomes what you call a point of inflation. So let's look at the distinguishing of stationary points using the second derivative method. For example, or that is to say, if the second derivative is going to be greater than 0, that means that coordinate x1 and y1 is going to be a minimum point. So whenever you substitute, as you are going to be handling the examples, and then you get your second derivative to be greater than 0, that means your second derivative to be positive. That means that the point you are dealing with is going to be called a minimum point. And if at all your second derivative is going to be equal to 0, then that one is called a point of inflation. Now if your second derivative is less than 0, that means that being negative, that's what we are going to call a maximum point. In the first example, you are going to be finding the coordinates of stationary points of the curve, which is represented by y being equal to 2x cubed minus 24x. And then we distinguish between them. We distinguish whether it's going to be a maximum point, which is like this, or it's going to be a minimum point. So first of all, remember that we identify maximum and minimum points by finding second derivatives. That means that we are prompted to find the first derivative. So y is given as this. So the second derivative, or the first derivative, which is dy dx, is going to be 6x squared minus 24. And then we make an outline that at stationary points, dy dx, or the first derivative, must be equal to 0. So we get the expression 6x squared minus 24 equated to 0. We divide through by 6, we remain with x squared minus 4 being equal to 0. But remember that this is a perfect square. So x squared minus 4 is the same as x plus 2 into x minus 2. Then that means that either x is going to be equal to negative 2, x is going to be equal to 2. Now since we're having two values of x, we are also required to find the corresponding values of y. So corresponding values of y, when x is equal to negative 2, y is going to be equal to 32. If at all we substitute in the expression that we had in the first place, the expression for y. So if x is equal to negative 2, y is going to be 32. And that means that our point there is going to be negative 2 to 32. And if x is equal to 2, then y is going to be equal to negative 32. And that means that our stationary point there is going to be 2 to negative 32. Now here, remember, we have only found the stationary points, but we don't know whether they are maximum or minimum. We don't know which one is maximum, and we don't know which one is minimum. So we shall proceed by finding the second derivative. So going for the second derivative, we are going to find y dx, second derivative in respect to x, which is going from the first derivative. If you differentiate this, you get 12x. And then we substitute for values of x only. So we get this point, the first point, and we substitute for x being equal to negative 2. And when we get the first point, which is negative 232, and you substitute for the value of x, we are going to get negative 24. And I told you, when you get your second derivative value being negative or being less than 0, that means that that point is going to be a point of maxima, or a maximum point. So you're going to conclude that therefore this one is going to be a maximum point. So we come back and we get the second derivative, and then we substitute for the value of x in our second point, which was 2 negative 32. So we shall substitute for 2. And putting 2 here, we are going to get positive 24. Now, since positive 24 is greater than 0, that point is going to be called a point of minima, or a minimum point. So we conclude that since second derivative is greater than 0, therefore 2 to negative 32 is a point of minima. 3 more examples under this one, you can call it a subtopic. So here in example 2, we are going to be investigating the nature of stationary points of the following curves. So for part A, y being equal to x into x squared minus 12. And part B, y being equal to x squared into 3 minus x. And then proceeding to part C, D and E. But here in this chapter, I've only done the first 2 examples. So you'll be required to do the other 3 as your exercise to examine your understanding. So starting with the solution for part A, remember that I told you first find y dx and then find at stationary point, or else the first derivative must be equal to 0. And this is going to help you to find the values of x. The values of x you have found are going to help you to find the values of y using the initial expression. So y is equal to this, so finding the first derivative, differentiating x cubed is going to give you 3x squared. Differentiating negative 12x gives you negative 12. And then you make a conclusion that at stationary point, or a condition that at stationary point, the first derivative must be equal to 0. So we equate our expression for the first derivative to 0. Dividing through by 3, you are going to remain with x squared minus 4. And that means we take x this side. Now here, you can either find square root, or you can expand this one in terms of perfect square. You end up with the same values. If you find square root, you're going to end up with plus or minus 2. And if you put it in terms of prime factorizing, you're also going to end up with plus or minus 2. So we find the corresponding values of y when x is equal to positive 2, and the corresponding values of y when x is equal to negative 2. So when x is equal to positive 2, y is going to be negative 16. And therefore our stationary point is going to become 2 to negative 16. And when x is equal to negative 2, we substitute that in the expression of y. And then you are going to end up with our y being positive 16. So the turning point is going to be negative 2 to 16 and also 2 to negative 16. But remember that we don't know which of these points is the maximum or minimum. That means that we have to go ahead and we find the second derivative. So in finding the second derivative from the first derivative, remember that this is our expression. So differentiating it the second time, we are going to get 6x. And then we substitute for values of x in both of these points. So if I substitute when x is positive 2, and you're going to get your second derivative to be positive 12. And we say that any number greater than 0, that point has to be a minimum, or a point of minimum. So we say that since you have got positive 12, point 2 to negative 16 is a point of minima. And then we also substitute for this point with negative 2 for the values of x in the second derivative. Doing that here, we are going to end up with 6 times negative 2, which gives you negative 12. And negative 12 is below 0, or is less than 0. And you say that any number less than 0, that means that that point given is a point of maximum. Last example, you are given y equals to x squared into 3 minus x. So first of all, we open brackets so that we can easen up our differentiation. So we opening brackets, we are going to end up with 3x squared minus x cubed. So we find the first derivative, which is going to be 6x minus 3x squared. And then we make a condition that at turning points, remember that turning points are the same as stationary points. So at turning points or at stationary points, always the first derivative or dy dx must be equal to 0. So we get this expression and we equate it to 0. So we are going to end up with 6x minus 3x squared being equal to 0. And then we prime factorize. Remember that we don't divide through by unknowns. We just prime factorize them out. So prime factorizing out the common factors across 6x and 3x squared, we are going to have 3x. So we shall remain with 2 minus x in our brackets being equal to 0. So it's either 3x being equal to 0, which will give us x being 0, or this bracket to be equal to 0, giving us x being equal to positive 2. Remember that after finding the values of x, you have to find the corresponding values of y. So when x is equal to 0, what will be the value of y? So we substitute for x, and then you will find that your value of y is going to be 0. So the first point that you're having is going to be 0, 0 as our first stationary point. And then you also get the corresponding value of y when x is equal to 2. And substituting for that in our expression of y, you're going to end up with y being equal to positive 4. And hence, our second stationary point is going to be 2 to 4 as our second stationary point. But you have to find the nature of these stationary points. Finding the nature of these stationary points, you are going to be required to find the second derivative. So our first derivative expression was 6x minus 3x squared. So second derivative is going to be differentiating 6x, you get 6. Differentiating negative 3x squared, you get negative 6x. And then we first substitute for the value of x using this point and also this one. So starting with 0, 0, you're going to find that your second derivative is going to be positive 6. Now since 6 is greater than 0, we make a conclusion that therefore that point is going to be a point of minimum, because we said any point giving us a value of second derivative above 0 is going to be minimum, and any point giving the value of second derivative being negative is going to be maximum. So substituting for 2 to 4, substituting for the value of x, which is 2, you're going to end up with 6 minus 6 times 2, which is going to give you negative 6 as the answer. And you're going to say that, but negative 6 is less than 0. And since negative 6 is less than 0, our point becomes a point of maximum. Next example, so here we are having our value of p being equal to 4s squared minus 10s plus 7. Now we are prompted to find the minimum value of p and then the values of s, which gives the minimum value of p. So notice the condition that they're using, a condition of what we call minimum. So here, first of all, we are going to say solution. So to find minimum values or maximum values in mathematics or in any other application, minimum and maximum, always the first derivative must be equal to 0. Just like we have been looking at the stationary and then the turning points. So first of all, we have to rewrite our expression, p being equal to 5 squared minus 10s plus 7. So we find the first derivative of p, which is going to be dpds. And you're going to end up with differentiating 5 squared, you end up with 8s. And differentiating negative 10s, you're going to end up with negative 10. And then you bring in the condition that for minimum value, provided what you're given, either maximum or minimum, or greater or least value of any unknown, the first derivative of that unknown must be equal to 0. So you get the expression that you have got and then you equate it to 0. So 8s minus 10 is going to be equal to 0. And then we make s the subject, which is going to be equal to 10 divided by 8. Reducing by 2, we end up with 5 divided by 4. And then we have to write back our expression. Because here, this quoting this value of minimum value has just enabled us to find the value of s, which was required. Now here, they have also told us to find the value of p, and p was given by the first expression. So you just have to substitute back for the value of s that we just obtained. So p minimum is going to be equal to 4 into, you just substitute for the value of s, because we are calling it p minimum because s, we have got it as being named the minimum value. That's why you're putting here p min. So substituting for the value of s, you end up with this expression. Simplifying further with your calculator, you're going to end up with 100 divided by 16 minus 50 over 4 plus 7. And adding up everything together, you're going to end up with 3 divided by 4. So finding the PDS, remember that the PDS, we found it as our first derivative to be equal to 8s minus 10. So we have got the value of p and we have got the value of s. So we need to know which kind of minimum or maximum does the second derivative give us a minimum value or a maximum value. Remember that for maximum value, the second derivative value must be negative, and for minimum value, the value of the second derivative must be positive. So finding the second derivative in respect to s gives us 8, because when you differentiate 8s, you are going to get 8. When you differentiate negative 10, you get 0. And this 8 is above 0. Now, since our second derivative value is above 0, we are going to conclude that, therefore, P is minimum when S is equal to 5 over 4, and the minimum value of P is going to be 3 over 4, just like we obtained it here. Let's enter more in the concept of maximum and minimum. Now, as we are navigating through maximum and minimum, always remember that for anything to qualify for being maximum and minimum, or least and greatest, that means that its first derivative must be equal to 0. But as we are dealing with these questions, know that you cannot differentiate when you're having two varying variables. For example, when you're having a cylinder, you're having R and H. You cannot differentiate when these two are existing in the same expression. In other words, you first express the expression either in terms of H and others being constants, or in terms of R and others being constants. So looking at example 4, we are looking at a cylinder can which is made such that the sum of the height and the circumference. Now remember that such expressions are the ones that are going to be helping you to express one value in terms of the other, to express R in terms of H, or to express H in terms of R. So they have told you that the sum of the height and the circumference of its base is going to be 45 pi centimeters. Now find the radius of the base of the cylinder if the volume of the can is going to be maximum. So you're going to start with our solution, and you're going to let the radius of the base to be small r and then the height to be small h, all of which are measured in centimeters. Now we call the condition that was given in that sentence because it's the one which is to enable us to convert one variable in terms of the other. We cannot have two variables in the same formula. So they told us that height plus circumference, summation of height and circumference is equal to 45 pi. So we substitute back our height, small h, and circumference of its base. Remember, when they're talking about base of a cylinder, its base is circular. So we find circumference of a circle since its base is circular. So that means that the formula of its base is the same as the formula of a circle. So that's why you're saying here pi plus 2 pi r being equal to 45 pi. Now we either make h or r the subject. But here it was easier to make h the subject since it's not attached to anything. So we take 2 pi r this side, and we end up with our equation 1 of h being equal to 45 pi minus 2 pi r squared. But remember that they told us that the volume must be maximum. That means that we are supposed to get dV we are supposed to differentiate volume in respect to either r or h. But since we have made h the subject here, that means that we are going to be differentiating in respect to h. So volume is equal to pi r squared h. Then we substitute for h because we cannot differentiate when both r and h are present. So substituting for h in this expression, you are going to end up with v being equal to pi r squared into 45 pi minus 2 pi r. So we always open the brackets so that we can ease our differentiation before actually differentiating. So we're going to end up with the expression of volume being equal to 45 pi squared multiplied by r squared minus 2 pi squared r cubed. Then we find the first derivative of volume in respect to r, which is going to be 90. We don't differentiate pi squared because it's a constant. We only differentiate r squared, which gives us 2. The 2 multiplies with the 45, which was present here, to give us 90. So 90 pi squared r minus 6 pi squared r squared. After differentiating this side, 2 pi squared are constant, but you differentiate the r cubed, which is going to be 3r squared. The 3 multiplies with the 2 to get it 6. And then we quote our condition that for maximum volume, always the first derivative in respect to any term they have given in the question, here they gave volume, must be equal to 0. So for maximum volume, dV/r must be equal to 0. Now we get the expression that you have got and then we equate it to 0. So we cancel out the constants. For example, we prime factorize out the common terms. And you're going to see that 6 pi squared r is going to be common. And then first of all, you can get rid of the constants, and then you just remain with r be in 2 brackets of 15 minus r. So either r is equal to 0 or 15 minus r is equal to 15. But remember, no radius can be equal to 0. So you eliminate that, and then you conclude that our radius therefore is going to be equal to 15 centimeters as required in the question. Now looking at the next example, we are saying that here, Onyango wishes to fence a rectangular farm. Now Onyango wants the sum of the length and the width of the farm to be 42 centimeters. I told you these are the expressions that help you to convert one expression in terms of the other, because you cannot differentiate when you're having both length and width in the same expression. So such sentences in the question are the ones that are going to be helping you to convert or to make one expression or one variable in terms of the other, so that you can differentiate. We only differentiate when we only have one variable. If your expression must either have width or length only, and any other thing must be a constant, so that the differentiation can proceed. So we are here. The question is, calculate the length and the width of the farm for the area of the farm to be as maximum as possible. Now we are going to be looking at the solution. So first of all, a rectangular farm, we make a sketch of a rectangle, and our width is going to be W, our length is going to be L. Now you're saying that here, the length and width of the rectangular farm to be L and W respectively, so that to let the examiner know that the terms or the conditions that you have used are not provided in the question, but you are letting them to be part of the question, which is a very good technique for any of you who wishes to take math serious. Now they say that now you make sure that you interpret the question the way it is given in the sentence. The sum of the length and the width. This is not multiplication, this was supposed to be addition. So we write it as it is in the sentence. Summation of length and width, they said is going to be 32. Then we make one variable in terms of the other, or we make one variable the subject. So making L the subject, we are going to take W this side, and then we remain with L being equal to 42 minus W. But remember that here they say that area of the farm must be as maximum as possible. So that means that we have to get to differentiate area in respect to either width or length. So we have to write the formula of finding area of a rectangle, which is given by length times width. So area substituting for length, because we can't differentiate when width and length are all present as variables. So we substitute for the expression of length, and then we end up with area being equal to 42 minus W into W. So opening the brackets, area is going to be equal to 42W minus W squared. Now we differentiate area since we only have our expression in terms of W only. So we differentiate A or area in terms of W or in respect to W. And differentiating 42W, you are going to end up with 42. Differentiating negative W squared, you are going to end up with negative 2W. And then we quote the condition for maximum and minimum items, and say that for maximum area, or for area to be maximum, the first derivative in respect to W must be equal to 0. So we get this expression and then we equate it to 0. So here we shall take 2W this side so that we can make it the subject, and we divide by 2 so that we get 42 divided by 2 so that we can get our width to be 21. Now we use the first expression where we made L the subject to find also the value of L, which is going to be 42 minus W. Substituting for that, you're going to end up with your L being 21 centimeters inclusive. Looking at example 6, here we are being told that the length of a rectangular block is twice its width, and then the total surface area is 108 centimeters squared. I told you that these statements given in the question are the ones that help you to express one variable in terms of the other. But this question is quite different, because you are being told that show that if the width of the block is going to be X centimeters, then its volume is going to be represented by this. And then find the dimensions of the block if the volume is going to be maximum. That means that you are supposed to differentiate volume. So first of all, we have to draw our tube. So solution, width, they let it to be X centimeter already. So drawing our tube, the width is X, and then they said the length is twice the width. which is going to be 2x. So the height was not described, we leave it as h. So we write the expression for finding volume because they talked about volume being maximum as possible and they gave the expression for volume. So volume is equal to length times width times height of a tube. And then when you substitute for that, our length is 2x and then our width is x and then our height is h. So we're going to end up with the expression of volume being equal to 2x squared h. But remember that they gave us the total surface area, and I've told you that such statements that are given help you to express one variable in terms of the other. So we find the total surface area. Now since this one was a block, finding total surface area for any tube is the same as twice into length, width height, and then plus height length. Substituting for that, you're going to end up with 2 into 2x squared plus xh plus 2xh. Now adding up everything and then opening up the brackets. We divide these two, we divide by 108 so that we can get 54. And then here we are going to end up with 2x squared, xh plus 2xh gives us 3xh. So substituting equation 2 into equation 1, so we make here h the subject from this expression. So making h the subject from this expression, we end up with that. We take 2x squared this side so that it becomes 54 minus 2x squared, and then we divide through by 3x so that we can make h the subject. And then we come back to our expression of finding volume, and then we substitute for h, because what they're telling us to prove here, there is no value of h, so it's what we substitute for. So substituting for h, you're going to end up with 2x squared into 54 minus 2x squared divided by 3x. So one of these x goes away with one of the x here, so that we end up with 2x into 54 minus 2x squared into 3. Now we try to make the expression in terms of the expression that was given in the question. So remember that the expression that was given in the question, we have here 4 in the numerator. And to get a 4 in the numerator here, we have to prime factorize out 2 from this bracket. And prime factorizing out 2 is going to multiply with these 2 here, so that you can end up with 4x. And then we bring these 3 outside, so that you can end up with 3. And we are going to end up with a bracket of 27 minus x squared. And this is what was required to be shown. Now the other thing was, volume was quoted to be maximum. So for volume to be maximum, the first derivative in respect to x must be equal to 0. So we have to find the first derivative of volume in respect to x. But before we do that, we have to make sure that the expression of volume is in terms which is easier to differentiate. So that means that we have to put this x back into this bracket. So doing that, we're going to end up with 4 over 3 into bracket of 27x minus x cubed. That you're going to end up with, we differentiate 27x because we leave 4 over 3 constant because it's a constant. We don't differentiate it. We only differentiate the inside bracket, which is having unknowns. So differentiating 27x, we end up with 27. And differentiating x cubed, you end up with negative 3x squared. And then we bring back our condition that for volume to be maximum, dvdx must be equal to 0. So we equate this expression to 0. First of all, we cancel this 4 over 3 because it's a constant, and then we shall remain with 27 minus 3x squared to be equal to 0. So we make 3x squared the subject by taking it this side, and after we divide through by 3, and we end up with x squared being equal to 9. So we find square root, and you're going to end up with your x being equal to either positive or negative 3. But in applications, we don't have negatives. So we ignore the negative 3 and only go with the positive. So using this, we find the value of length. Length was equal to twice the width, which is 2x, which is going to be 2 times 3 to give us 6 centimeters. So height, the expression for finding height was this in equation 1. So we substitute for x by putting 3 where x is, and putting everything in the calculator, you're going to end up with 54 minus 18 divided by 9. And your height finally is going to be 4 centimeters. So looking at example 7, we are going to be looking at a cylindrical volume, which is V. We're saying that here, a cylindrical volume V is to be cut from a solid sphere of radius R. So this radius is going to be capital, implying that it's going to be somehow constant. So prove that the maximum volume of the cylinder V is going to be given by this expression. So volume must be equal to 4 pi R cubed divided by 3 root of 3. Now looking at the solution of this, we are going to say that let the height of the cylinder be h, which is going to be small h. For that, you are going to draw our solid sphere, and then you are going to inscribe our cylinder. So note that the radius of this solid sphere was given as r, and this r is going to go up to the center, not where it's starting from. It's starting from the edge of the circle itself. But here we are going to try to extrapolate in form of a small rectangle. So the whole of this is going to be the height of the cylinder. So we divide the cylinder divided by 2 so that we can get a right angled triangle in this form. And the height of this right angled triangle, or the opposite, is going to be h divided by 2. Since we got the whole height of the cylinder and we divided by 2. And then the hypotenuse is going to be capital R. And then the adjacent is going to be r, which is the radius of our cylinder. So here the question, capital R is going to be constant because capital R is the radius of the sphere. It's not the radius of the cylinder that we are dealing about. So the only variables that we're having small r and then small h as the only variables. So for us to differentiate, we should get an expression to make either r or h the subject, so that we can differentiate when the two are not existing in the same expression. And to do that, we are going to be using Pythagoras theorem. So using Pythagoras theorem, we say that to get the hypotenuse, we get the adjacent squared plus the opposite squared being equal to hypotenuse squared. And then I told you that the only variables we have in here is small r and then small h. So we leave capital R as a constant because capital R is for the sphere and you're only dealing with the cylinder as the question required. So from Pythagoras, we open the brackets. So this is going to be r squared plus h squared divided by 4 being equal to r squared. So having that, we make r squared the subject because it's easier to make r the subject as compared to h squared. So r squared is going to be equal to r squared minus h squared divided by 4. So we need to get, they say that volume must be maximum, and for volume to be maximum, we need to differentiate volume in respect to either small h or small r. But the expression for finding volume of the cylinder is given by pi r squared h. So we substitute for r in this expression, say that our expression is all in terms of h, so that we can differentiate. So substituting for r, we are going to end up with this expression. So opening the brackets, we are going to end up with your expression of volume to be pi r squared h, then minus pi h cubed divided by 4. But remember that this r squared is considered to be constant since it belongs for the sphere, not the cylinder. So you are free to differentiate since our expression is in terms of h. So we differentiate in terms of h. So we find the v of first derivative of volume in respect to height. And since pi r squared is constant, we leave it out. We only differentiate h, and you are going to end up with pi r squared. Here, you only differentiate h cubed, and you are going to end up with negative 3 over 4 pi h squared. So we call the condition that for maximum volume, first derivative of volume must be equal to 0. So equating the expression that you have got to 0, and then cancelling out the constants. We cancel the constants, which is going to be pi, and then you make h squared the subject. You're going to end up with 4r squared divided by 3. Now we want only h, so we find the value of h only by finding square root on both sides. But here we are not interested in negatives. Whenever you're finding square root, it's either positive or negative, but in applications of differentiation, we ignore the negatives. So that's why we only go with the positives. So h is going to be equal to, finding square root of the numerator, you are going to end up with 2r, and then square root of the denominator, you are going to end up with root of 3. So we record back the expression of finding volume, since they wanted the expression for finding volume, or Vmax, and then we substitute for the value of h. So substituting for the value of h, you are going to end up with this expression. But remember that we also had the value of r also having an expression, which was this. So we come back to this expression and we also substitute for the value of h in this expression. So substituting for the value of h in the r squared expression, you are going to end up with r squared minus a third r squared. So making r squared, the small r squared the subject, you're going to end up with 2 over 3 r squared. So we write back our expression of finding volume and then we substitute for both h and we also substitute for r squared. So doing that, you're going to end up with your V max being equal to substituting for h, for r squared, and also substituting for h. Multiplying everything in the numerator, you're going to end up with 4 pi r cubed divided by multiplying everything in the denominator, you're going to end up with 3 root 3 as your final answer. In example 8, we're having a cylinder inscribed in a hemisphere this time of radius r as shown in the figure below. So this hemisphere, remember that so the question is going to be finding maximum volume of the cylinder, which is in terms of r. But remember that this hemisphere has been given a radius of r. So we find a point which is in approximation with our cylinder, but when it's starting from the curve of the sphere, and then we take it to the center so that we can find the volume of the, or we can find the radius of the sphere. But this, bear in mind that as we are finding base of this hemisphere, we are also finding the hypotenuse of our cylinder, and then the height is going to be represented by h of our cylinder. So we end up having a small right angled triangle, with this one being our h and then r being the radius of the sphere. Therefore it's going to be constant since it's the radius of the sphere. Then we let our radius of the cylinder to be x. So down here is going to be x, and then by Pythagoras theorem you see that x squared plus h squared is going to be equal to r squared. And then remember that here the only variables you're having is going to be the height of the cylinder and then the radius of the cylinder, which is x and h. So we aim at making one the subject. So I made x squared the subject, having r squared, having x squared being equal to r squared minus h squared. And then we call the volume of the cylinder, is equal to pi r squared h. But our r in this time around is the same as x. So we end up with the volume being equal to pi x squared h. We substitute for the value of x so that you can differentiate, because the only variables you're having is x and h. So we want our expression to be purely in terms of h. So we substitute for x squared, and then we shall end up with r squared minus h squared multiplied by h. We open up the brackets and then you end up with the expression of volume to be pi r squared h minus pi h cubed. Now since our expression is in terms of r, remember that r is for this hemisphere and we don't have x, we only have h as the variable, we are free to differentiate. So we find dvdh. Dvdh here, since pi r squared is a constant, we only differentiate h, so remain with pi r squared. Differentiating h cubed, you end up with negative 3 h squared, and then with a pi which was constant. Then we bring in our condition that for volume to be maximum, or for maximum volume, the first derivative must be equal to 0. We equate the first derivative expression to 0, and then we factorize out the common item, which is pi. Remember that pi is a constant, so you can easily get rid of it. So we make r squared the subject by taking 3h squared this side, and then dividing through by 3, and you're going to remain with h squared being the same as r squared divided by 3. Then to remain with h, we find square root on both sides. And finding root on both sides, you're going to end up with r here divided by root of 3. And then we come up with the expression, because we have our h already found. So we come up with the expression for finding the value of x, which was the radius of our cylinder, which was given from Pythagoras theorem as r squared minus h squared. So we substitute for h squared, which is the same as r squared divided by 3. So collecting LCM is going to be 3. This is the same as 3r squared minus r squared to get 2 out of 3 r squared, and that's your x squared. So the expression for finding volume of a cylinder, we'll rewrite it again as pi x squared h, and then x squared being equal to 2r divided by 3. Remember that this is 2r squared. and then h is equal to r divided by root 3. So we come and we substitute everything here so that we can get our maximum volume. So x squared is the same as 2r squared divided by 3, and h is the same as r divided by root 3. Multiplying everything, you're going to have in the numerator 2 pi r cubed divided by 3 root 3. So looking at example 9, we are going to have a rectangular block with a square base of x centimeter. Square base, that means that all sides of the base are going to be equal. So length and width are the same. And then its surface area is 150 centimeters squared. This is the sentence that is going to help us express one variable in terms of the other. Now prove that the volume of the block is going to be given by the formula 1/2 into 75x minus x cubed. And then part A, calculate the dimensions of the block provided the volume is maximum. And part B, calculate the maximum volume. So let's look at the solution. Made our sketch of a tube, but this tube must have a square base. Square base means that length and width are the same. So if length or width is x centimeters, also width has to be x centimeters. And then the height was not given, so we leave it as h. But remember that we are given surface area, and to find surface area, total surface area of a tube, just like the formula is provided in the logbook, is the same as length width, twice of length width, width height, and then height length. And then you substitute for the surface area, which is given as 150 centimeters squared. So length width is the same as x squared. Width height is going to be the same as xh, and then height L is going to be the same as xh. So adding xh and xh, we are going to end up with 2xh. We divide these two by 150 so that we can remain with 75. So 75 is going to be equal to x squared minus 2xh. So we make h the subject, since it's easier to make the subject. So making h the subject or h the subject, we're going to end up with the expression of h to be equal to 75 minus x squared divided by 2x. Then we come back and rewrite the expression for volume, because they told us volume must be maximum. That means that we have to differentiate volume in either respect to x or respect to h, because they are the only variables that we are having in our diagram. So finding volume of a tube is the same as length times width times height. And our length and width are the same as x squared, and then height remains the same as h. So we substitute for the value of h as we got it above here. And you're going to end up with this expression. So opening the bracket, one of these x is going to go with one of the x here, and then you're going to end up with a half x into 75 minus x squared. But for us to differentiate, we have to first make it in terms of a way easier to differentiate. So we have to put the value of x back inside the bracket. And we end up with our value, or the formula of finding volume, to be a half into 75x minus x cubed. So we find the derivative here, since this one is easy to differentiate. So dvdx is going to be equal to a half, we leave a half constant, and then you differentiate the inside bracket. So differentiating 75x, you end up with 75. Differentiating negative x cubed, you end up with negative 3x squared. And then we got our condition that for volume to be maximum, the first derivative of volume must be equal to 0. So we equate the expression for first derivative to 0. A half is going to leave, so that we remain with 75 minus 3x squared to be equal to 0. And then we take 3x squared this side to make it the subject, and we divide through by 3. 75 divided by 3, we are going to end up with 25. And then we find square root on both sides. Square root is always giving us positive or negative, but in applications we ignore the negative side and we only consider the positive part. So x is going to be equal to 5 centimeters. So we find the value of h, since we have already found the value of h. So doing that, we record back the expression for finding the value of h, which we already got here. So substituting for x, we are going to end up with 75 minus 25 divided by 10. And that is going to be the same as 50 divided by 10 to get you 5 centimeters as your height. At example 10, we are going to be looking at part A to be a variable rectangular flower garden has a constant perimeter of 40. Now we are going to be finding the length of the side when the area is maximum, and in part B, a variable rectangle with a constant area which has been given as 36 centimeters squared. We are supposed to find the length of the sides when the perimeter is going to be maximum. So starting with part A, first of all, we have to sketch our rectangular flower garden. And we are going to let the width to be W and also the length to be L. Now they say that the perimeter for all this is 40. Now the 40 is what is going to enable us 40 is what is going to enable us to convert either W in terms of L or L in terms of W. So perimeter of the flower garden is given by, this is the formula in the logbook. Perimeter is given by twice into length plus width. But the perimeter here was given as 40. So we use this perimeter, which was given as 40, to express W in terms of L or L in terms of W. So we shall end up with 40 being equal to 2 twice into length plus width. So you divide through by 2, and then you end up with 20 being equal to length plus width. And then you make length the subject, and you're going to end up with L being equal to 20 minus W. And then since they talked about area being maximum in the question, that means that you're supposed to differentiate area. So area is equal to length times width. And then we substitute for the expression of length, and you're going to end up with area being equal to 20 minus W into W. Opening the brackets so that you can easily differentiate, we are going to end up with the expression of area to be 20W minus W squared. So we find the derivative of area in respect to W, and you're going to end up with 20 minus 2W. And then you call the condition that for area to be maximum, the first derivative in respect to W must be equal to 0. So we're going to end up with 20 minus 2W to be equal to 0. We take 2W this side and divide through by 2, you end up with your W being 10. Then to get L, we get this expression in which you made it the subject, and then you substitute for W. And also your length is going to be 10 centimeters. Now looking at part B they talked about perimeter being maximum. That means that you're supposed to differentiate perimeter. And they gave area so that we can make length or width in terms of the other. So we're going to say that perimeter of a rectangular flower garden is given by this expression. But area, which was given, is given by length times width. So we make length the subject, and we're going to end up with 36 plus W. So we substitute for expression of L in the standard formula of perimeter, and you're going to end up with P being equal to 2L is 36 over W plus W. So opening the bracket so that you can easily differentiate, you're going to end up with 72W plus 2W. Then here we can easily differentiate, and differentiating this, the W is, you're going to end up with negative 72 divided by W squared and then plus 2. But remember that for perimeter to be maximum as quoted in the question, we have to equate the first derivative of perimeter to 0. It's saying that dp in respect to W is going to be equal to 0. Getting the expression and equating it to 0, putting to this side and cross multiplying, you're going to end up with 2W being equal to 72. And then you divide by 2, you're going to end up with W squared being equal to 36. Then you find square root on both sides, you're going to end up with W being equal to 6. And then use the expression where we made L. Remember that L is equal to 36 divided by W. And therefore W is 6. So if you get that 6 divided by 6, you're going to end up with 62. So width is 6 centimeters, and then length is also 6 centimeters. Now let's look at example 11. In example 11, Mukasa wishes to enclose a rectangular piece of land, provided it's of area 1,250 centimeters squared, whose one side is going to be bound by a straight riverbank. And then we are supposed to find the least possible length of the barbed wire. Now this question is indirectly asking for the least or minimum perimeter, least possible length of the barbed wire, the total barbed wire which was used, which is the same as perimeter. Now what they gave in the question, they gave area. So the area they gave in the question is what is going to enable us to express one variable in terms of the other. That's why we say that if at all the length is going to be x and the width is going to be w or y, xy is going to be equal to 1250. So making y the subject, we're going to end up with 1250 divided by x. Now finding the perimeter of this rectangular piece of garden, provided one side is not going to be enclosed, total perimeter is going to be equal to y plus y and then plus this x up here. So you're going to end up with perimeter being equal to x plus y, which is going to be perimeter being equal to x plus 2y. So substituting for y, you're going to end up with this expression. Simplifying everything, you're going to end up with a perimeter expression being equal to x plus 2500 divided by x. Then we find the derivative, since this one can easily be differentiated. Derivative of x is going to be 1. Derivative of 1 minus x is the same as negative 1 divided by x squared, which multiplies to 2500 for us to end up with that expression. And then you call the condition that for length to be least or minimum, then the first derivative must be equal to 0. So equate the expression to 0, and you try to make x squared the subject. We shall take the other side of the curve so that we remain with this expression, and then we cross multiply and then remain with x squared to be equal to 2500. We find square root on both sides to end up with x being equal to 50 centimeters, and then we use the expression of y, which already got earlier, and then we substitute for x to get the expression, to get the value of y, which is going to be 25 centimeters. Now let's look at example 12. In this example, we are being told that a closed right circular cylinder of base radius r centimeters and then height h centimeters has a volume of this 54 pi centimeters cubed. Now show that S, which is the total surface area of the cylinder, is going to be given by this expression. Hence find the radius and the height, which makes the surface area to be minimum. Now for this, we are going to first sketch our right circular cylinder. And it's going to have the radius r, and its side is going to be denoted by h. And we are going to say that the volume, finding volume of a cylinder, since they talked about its volume here, that means that we are supposed to use its volume to convert either r or h in terms of the other. So volume of a cylinder is given by pi r squared h. So substituting for the volume which was given as 54 pi, is going to be equal to this expression, pi r squared h. And then we either express r squared or h squared in terms of the other. So first of all, pi is common, is going to cancel off. And then we divide through by r squared to make h the subject. And therefore h is going to be equal to 54 divided by r squared. Come back and say that surface area of a cylinder, therefore area is going to be equal to, is got by. Remember that for a cylinder, it has two circular bases. The circle which is closing its top and the circle closing its bottom. And the area of this circle is got by pi r squared. So since there are two, we get it by saying it's going to be 2 pi r squared h. And then since it has this half, there is this half, we find the area of that by pi r h. Because this is r and then this is h. So we multiply it by r. And then plus the second half, which makes up the full cylinder. That's why you're having pi r squared plus 2 pi r h. So you substitute for the value of h which you have made the subject, and you are going to end up with 2 pi r squared plus 2 pi r into 54 divided by r squared. And if you do that, you're going to end up with your r, with your 2 pi r squared, then plus 108. But remember that this is not, there's no power here, because this r here cancels one of the r and you remain with just r, so that your value of your expression of area is this. Now this, since this one is easier to differentiate, we can differentiate. Differentiating 2 pi r squared, you end up with 4 pi r, because the 2 multiplies with this 2 to get you 4, and then the pi is constant. So 4 pi r minus 108 divided by r squared pi, because when you differentiate 1 divided by r, you end up with negative 1 divided by r squared, which affects the whole expression. That's why its sign changed from positive to negative. So we say that here, after finding the derivative, we say that for surface area to be minimum, the first derivative must be equal to 0. So equate this expression over to 0. And we find a way of making r the subject. And we are going to do that, first of all, by multiplying through by r squared, so that we get rid of the denominators. So multiplying through by r squared, you're going to end up with 4 pi r cubed minus 108 pi, then being equal to 0. And then you make r cubed the subject. So it's going to be 108 divided by 4. Remember that the pi's cancelled out each other since they are constant. And when you divide 108 divided by 4, you're going to get 27. Finding cube root on both sides, you're going to end up with your expression of r, or value of r to be 3 centimeters. So we find the value of h since we have already found the value of r, which was the only variable present. So h was got as 54 divided by r squared, and this is going to be the same as 54 divided by 9, since 3 squared is the same as 9. So you end up with 54 divided by 9, you get 6. So your value of h is going to be 6 centimeters, and you already have solved the cylinder is going to be 3 centimeters. So looking at another example, we are provided that the company that manufactures dog food wishes to pack the feed in closed cylindrical tins. What should be the dimensions of each tin if each is to have a volume of 250 pi centimeters cubed and the minimum possible surface area? So here we are going to first say that area for that tin is going to be given by this 2 pi r squared, because this tin is enclosed by 2 circular bases, and then plus 2 pi r, which is the total surface area of an open cylinder. And then the volume is got by pi r squared. This is the volume of a cylinder. So since it was given, it's what we are going to use to express either r or h in terms of the other. So a substitute for volume is going to be 250 pi, being equal to pi r squared h. So we make either h or r squared the subject according to you. So here I made h the subject to get 250 divided by r squared. So I come back to this expression of finding total surface area, and then I substitute for h, so that I can have the only variable in my expression as r, so that I can go ahead and I differentiate. So here we are going to have 2 pi r squared plus 2 pi r into 250 divided by r squared. Doing that, further simplifying, we are going to end up with 2 pi r squared plus 500 pi divided by r. Then we are going to find the derivative. Differentiating this 2 pi is constant, we only differentiate r squared. So we are going to end up with 4 pi r. And then differentiating 1 over r, since 500 pi is a constant, you end up with negative 1 divided by r squared, which multiplies the constant to end up with this expression. After finding the derivative, you make a condition that for surface area to be minimum, its first derivative must be equal to 0. So we get the whole expression and then we equate it to 0. So we multiply through by r squared, and then we prime factorize out the common thing. So multiplying through by r squared, you're going to end up with 4 pi r cubed minus 500 pi being equal to 0. And then you prime factorize out pi since it's common. Now since it's constant, it can easily be crossed or divided by 0. So we make 4 pi r cubed the subject by taking 500 this side of the equal sign, and it's going to be positive, and then we divide through by 4. 500 divided by 4, you're going to end up with 125. Now we find cube root on both sides, and cube root of 125, you're going to find that it's going to be 5 centimeters. So the height, we already got the expression of height to be 250 divided by r squared, and r squared is going to be 5 squared, which is the same as 25. So it's the same as 250 divided by 25 to get you your value of height of the cylinder to be 10 centimeters. Now the next example, which is a UNEB question, is going to be your assignment. You try to do it out and then you reach out to your teacher for guidance, or you combine with your colleagues so that you can try to interpret the question and you answer it. So pause the video and you write down the question. And that's your assignment. At the end of this video, we are going to be proceeding the next video handling small changes still under applications of differentiation. Now you advise to share the video to your friends so that you can all benefit and discuss together after studying. Those of you having papers or exams, success in your examinations.